Welcome to our talk named Rage Against the Machine Clear, a systematic analysis of machine clears and their implication for transient execution attacks. This was a joint work with me, Enrico Barberis, and Hany Ragab, and our professors Herbert Bos and Cristiano Giuffrida. And all of us are coming from the VUSEC security group in Amsterdam. Today we're going to present in these slots. We start with some background. Later we're going to focus on the main topic of the presentation, that is machine clears. And later we're showing a full end-to-end exploit on Firefox with a demo. And finally we conclude with some results. Before deep diving into machine clears, let's have a small background section. And all this work is based on side channel. So, what is a side channel? In a nutshell, an attacker, by observing side effects of a system, can infer some secret data. For example, here, with a stethoscope, an attacker can hear the safe and discover the secret combination to open the safe. Again, this is not an intended communication channel, it's a side effect, but still, we can use this leakage of information to obtain information. But all these apply to modern processors. So, before we saw a sound side channel, On processor, usually we use timing side channel. It is way more reliable. And the most common way to observe this kind of leakage of information is through flash and reload attack. So let's have a very simple example to explain it. We have the data cache that is on the bottom, where we have some entries of an array stored in this cache. So the green one will be cached and the gray one will not be cached. At the beginning, some entries will be cached, some other entries will not. The first step is to bring this cache to a known state, by, for example, flashing the entire cache. Then the victim will execute a snippet of code, for example, like this one, that depending of a secret value, so a bit of a crypto key, will either access array 0 or array 1, for example. And let's say that in our example, we are accessing the first entry of the array, so array 1. And this will bring array 1 into the cache. Later, the attacker, by performing the reload step, will measure the timing for every access time for each entry of the array. So the first one, that was never accessed, will be quite slow. The second one, instead, since was loaded by the victim, will be much faster. And just by measuring this delta time between slow and fast, an attacker can observe what the victim executed, thus leaking the key. But all these actually become very interesting is with transient execution or speculative execution. So let's combine this cache side channel with speculative execution. Let's look at this simple snippet of code, a very common piece of code, so bounded array access. So before accessing an array, you're checking that it's in the bounded size. And let's suppose that the array size, for some reason, for example, is coming from a long memory operation, is not available immediately. The processor must it will prefer to speculatively execute the inner branch of the inner code of the branch to optimize the speed execution. So the processor is betting that the branch will be taken and the memory access will be executed. But this is indeed a speculation. What happens if this is a wrong one? Well, the processor must revert the execution and roll back to the other branch to execute. But still, as you can see in this slide, the array at position X is still in the cache. So this trace is still there. An attacker can still discover this, observe this side channel, And as you can see, combining these two primitives, so speculative execution and side channel, an attacker is not only capable of observing what the victim is executing, but also to observe what the processor is executing in a speculative path, so a wrong path that is never committed. And again, we can recover what the processor did, again, using the timing side channel. Just with these two primitives, in the last years, many attacks were discovered. Let's start by late 2017 with all the most famous Spectre and Meltdown that probably all of you know. And after that, month after month, new attacks variant popped up. For example, in 2019, micro-arithmetic data sampling brought a lot of variants, as you can see, where basically an attacker can basically can break every barrier in the single physical core. For example, we had riddle, load value injection, and many other attacks. Then, after 2020, we even crossed this border by leaking across multiple cores on the same CPU die. And now, we are presenting two new complete attack primitives that are named floating point value injection and speculative store bypass that we are going to present today.
All right. So let's look first at the main class of all these transit execution attacks. So here, Intel defines bad speculation as the root cause of discarding issued microoperations on x86 processors. And it defines this bad speculation in two main subclasses. The first one is branch misprediction, which we just saw. And it's basically when a branch predictor mispredicts either the direction or a target of a branch. And the second class is machine clear, where a machine clear condition, when it occurs, it flushes the entire pipeline and resumes the execution from the last retarded instruction. So it's not waiting to mispredict a branch. It's a deterministic condition that once it occurs, it flushes the entire pipeline and resumes from the last retarded instruction. Well, branch misprediction have been widely explored on, for example, Spectre, and along with different types of faults and different ways of aborting an Intel TSX transaction, all these three methods have been widely explored in all previous transit execution attacks. The class of machine clear remains widely unexplored until now. So everyone that wanted to create a transit execution path, it had either to create a fault or abort an Intel TSX transaction or mistrain a branch predictor and mispredict. But no one explored the other ways of creating these transit execution paths that fall under the class of machine clear. And this is what we did in this work. So in this work, we performed the reverse engineering, the security analysis of the four main types of machine clear, which are self-modifying code, floating point, memory ordering, and memory disambiguation machine clear. Two of these four types of machine clear led us to obtain a completely new transit execution attack-based attack primitive. The first one is called speculative code store bypass, which is based on a self-modifying code machine clear. And the second one is called floating point value injection, which is based on top of a floating point machine clear. Furthermore, the floating point value injection attack primitive led us to mount an end-to-end exploit, leaking arbitrary memory addresses inside the Firefox web browser with a leakage rate that can reach up to 30 kilobytes per second. So in order to understand all these types of machine clear and how a machine clear can actually work, we first try to understand what is the architecture invariant upon which machine clear is based, how this invariant can be violated and therefore triggering a machine clear or a pipeline flush, how this invariant violation, what is the security implication of this violation, and finally, how this violation can be exploited. So the first type of machine clear that we are going to look at is self-modifying code machine clear. And a self-modifying code is a program storing instructions as data, modifying its own execution, modifying its own code while it's being executed. Let's take a look at this example, this snippet of code where we have two instructions. The first instruction is modifying the following instruction, changing it from a load secret to a no operation. Modern front end of modern CPUs in order to maximize the execution throughput, will fetch, decode, and execute speculatively well ahead of retirement, well ahead of the architectural retirement point. And whenever a front end of modern CPU will detect a store instruction trying to modify code that has been already fetched, decoded, and executed, so it's already residing in the pipeline, it will have to flush its pipeline from the previously and speculatively execute an instruction, in this case the no operation, in this case the load secret that was already in the pipeline, and fetch the code and execute the new code that is being stored, in this case the no operation, because this is what the program is doing. It needs to modify the code, and therefore the instruction stream inside the front end. But since this detection of a self-modifying code is not immediate, this creates a transient window, or some time window where the CPU has already fetched, decoded, and executed the stale code, which was already in the pipeline, in this case the load secret. And as we saw earlier, through a covert channel, we can leak the side effects of this stale execution of the load secret. And therefore it will try to flush its pipeline from the stale code and try to execute the new code. So the architecture invariant here is that store instructions always target data memory addresses. This architecture invariant is violated in the case of self-modifying code, which does exactly the opposite, where it targets code memory addresses instead. This invariant violation allows an attacker to transiently execute stale code, which is in this case the load secret. And in order to understand how we can exploit such behavior, we need to understand what is the attack primitive that this type of machine clear provides us with. So speculative code store bypass is an attack primitive that is built on top of a transit execution window created by a self-modified code machine clear, which allows an attacker to execute stale code under its control. Let's take a look at the three main steps of this attack primitive. But first, keep in mind that code and data views are always coherent between each other, and there are two different views of the same memory, of same addresses. So in the first step of SCSB, we JIT the code of function f to perform the store step of a self-modifying code, where we need to store code and then execute it. In this case, to store code under attacker control, we JIT a function f. And we JIT it at the same address where the code of function g is already residing in memory. In this case, we do it through data, because this is how self-modifying code works. It tries to store code as data. The second step, as we see here, we are creating a temporary desynchronization between code view and data view, where the code view will continue to contain the previously fetched, decoded, and executed code, which is function g. But the data view will contain the freshly stored code, which is, in this case, function f, creating this temporary desynchronization between code and data. Eventually, the CPU will detect that there has been self-modifying code and will issue a machine clear flushing its own pipeline from the previous and stale code, which is, in this case, function g. So yeah, at this step, even before flushing the pipeline, if we get to the point that we have actually to call the function that we just stored, the processor will take the code residing at that address from the code view. It will not take the one that we just wrote in, because it has no notion at this point of a self-modifying code. So it needs to fetch whatever was in the code view, execute it transiently, then trigger machine clear, then as a last step, resynchronize code and data to resume the coherency that was there before the self-modifying code program. So during our reverse engineering of this behavior, we looked at the developer manuals of Intel to see how they suggest to handle self-modifying code and cross-modifying code on their processors. And we see that there are basically two options to handle this. And interestingly, option one that Intel is suggesting to users in order to handle self-modifying code and cross-modifying code is describing the exact steps of our attack primitive, which means that any program or any software relying and adopting option one to handle self-modifying code is speculatively performing a speculative code store bypass attack without knowing this. Because, again, option one is relying on the fact that code and data are coherent all the time. This is true on the architectural side, but on the microarchitectural side, this can be violated. This coherency can be broken in the case of a self-modifying code. In fact, the two main web browsers used by millions of users are basically not performing any operation whatsoever when they try to store new code, which is the exact use case of our attack primitive where an attacker control code can be used. So an attacker can JIT whatever JavaScript code they want, which will be stored, so creating and performing the store step of a self-modifying code, and later at some point this JITted code will be executed, and therefore execute stale code. And as we can see here, both Chrome and Firefox are not doing anything to avoid this behavior, because they are relying on option 1 that Intel is suggesting in their own in the developer manual. So for exploiting SMC, we have speculative code store bypass, which allows an attacker to execute stale code, which is somehow similar to its architectural counterpart, user-free attack primitive, where an attack is accessing a memory that is not referenced anymore. The second type of machine clear that we're looking at today is called memory ordering machine clear, which is based on a total store order model, memory model, which is the one adopted by and implemented by Intel in their CPUs. Which is a memory model that guarantees that all CPU cores see all memory operations as the program order, except one case, where a store instruction followed by a load instruction operating on different addresses. These two may be reordered, so violating the program order. Let's take a look at this example, where we have processor A performing 2 load instructions, and then a function call on the resulting loaded value. And processor B is performing 2 store instructions on the same addresses that processor A is loading. So let's assume that for some reason, the first load of processor A is slow, because, for example, it has a cache miss, so it needs to fetch the data from main memory. That will take time. Processor A will not wait internally for the data to come from memory, and will execute out of order the second load and all subsequent dependent operations. So in this case, the second load on address Y and all subsequent operations will be executed out of order and will be kept in a ready-to-commit state internally in processor A, waiting for the data of the first load to be fetched and then commit everything in program order to follow the memory model of the CPU. Let's assume that at this point, processor B performs its corresponding store instructions, modifying the value of X, address and address Y, which processor A have already loaded out of order. At this point, processor A cannot commit previously and the speculatively loaded value of address Y, and it needs to flush its line from the speculatively loaded value, take into account the new value of Y that is stored by processor B, re-execute the second load and all subsequent dependent operations. So as we can see here, we loaded a stale value from memory by violating the memory order model. So the architecture invariant of this type of machine clear is that out-of-order execution always complies with the total store order memory model. This architecture invariant is violated in the case of a memory ordering machine clear, where 2 processors can violate each other's program order. This violation allows an attacker to transiently leak stale data, in this case, the old value of a memory address. And this type of machine clear is non-trivial at all to exploit. We tried many times, but it's not easy due to the strict synchronization between the 2 cores that need to be so precise, even more on the microarchitectural level, to violate the memory order model. Now we'll hand over to Enrico, who will tell you more about this third type of machine clear we're presenting today.
Okay, thank you. Yeah, now we're going to talk about floating point machine clear. This one is the one that led us to find a full end-to-end exploit on Firefox. And it's completely based on a spatial representation of floating point numbers that are named subnormal. And usually they are very small numbers. For example, for the double floating point representation, every number below 2 to the power of minus 1022 will be a subnormal number. But to keep it simple, let's say that in the IEEE standard floating point, they decided to create a very, let's say, special and complicated representation of small numbers. And there will be a machine clear on this. Again, let's use a snippet of code to explain this more easily. let's suppose we have some floating point operation, so a division followed by an addition, very common snippet of code. And basically every time the following is happening. So the the floating point unit is performing a division. But since the floating point unit must be fast, it's always operating on normal numbers, on the, let's say, standard floating point numbers. It's always betting that this special representation never kicks in, basically. So it quickly performs the floating point division result, and it will forward this value to the subsequent instruction, for example, the addition. But let's suppose that actually this division generates a very small number that is in the subnormal range. Later, the floating point unit will detect this, and basically it needs to stop the entire processor because it generated a completely wrong result, and it will basically trigger a machine clear by flashing all the subsequent instructions. And again, to compute the correct result, the processor actually relies on software. There will be a microcode assist, and this division will be actually very slow compared to a normal division. So the processor, again, will compute this division in software, generate the correct result, and give it back to the CPU with the intended operation result. So here we see that basically the floating point unit, to be fast, is optimized for normal floating point representation. And subnormal is treated as a special case that you need to handle separately. To violate this is super simple. You just need to make a floating point operation that generates a very small number. And the security implication here is that the wrongly computed result, the one that is using the red instruction, is almost completely under attack control. So an attacker, by choosing the operands in a specific way, you can transiently inject some arbitrary values to the subsequent instruction. And for exploitation, we are going to show you now the full exploit that we made to Firefox, and we name it floating point value injection. Okay, this is a Firefox version 83, if I remember correctly. On the left, you have an origin that is different from the iframe to the right. So the victim is on the left, the attacker on the right, completely separated. And the goal here is from the attacker iframe, let's suppose it's another advertisement of a web page, is to leak the entire content of the other page. Now, let's go back for a moment to this arbitrary value injection. So we develop a tool that is available on GitHub, where you just provide the value that you want to see transiently on the floating point division in this case. And this tool will give you the X and Y operand of the division. That transiently, as you can see, will give you the deadbeef, for example, here, the transient result as you wish. Again, please notice that the real result, the architectural result, here is minus infinity. But actually, the processor, when computes this wrong result, will obtain the results on the bottom that you can see. Now, if you notice, we also have FFB on the top of the floating point number. Why is the case? Well, on Firefox browser, specifically in the JavaScript engine, every object variable is represented with a floating point numbers. And this technique is named non-boxing. And it's quite simple. So in the unused space of floating point numbers or non-numbers, the top bits, FFB, this is the encoding for the type of the variable. So in this case, this means that it's a string object. While the bottom, deadbeef000, is the payload, basically the pointer to the string. So let's suppose that we use the X and Y operands that we found before. We perform the division, and then we ask the JavaScript engine, hey, is the type of the division string? Obviously, the answer is always no. I mean, if you operate on numbers, the type of the variable should be integer. And indeed, architecturally, the processor executes the blue branch, taking the else case. However, speculatively, we injected this FFB deadbeef result, again a string where we control the pointer. And the JavaScript engine, at the beginning, will say, well, of course, the division of these numbers is a string. And we control the pointer of the string. So by accessing, for example, the length parameter, we are forcing the JavaScript engine to read whatever we want. And then using the flash and load attack that we explained before, we can then recover this data later with a state channel. So again, here, if you think about it, it's pretty crazy that we managed to type confuse JavaScript, that a division result is of type string, and on top of this, we control the pointer bits. So we managed to build a read primitive. You can read any address in the Firefox process, just starting by a division. And yeah, usually we're used to that. At least the CPU on mathematical operation is perfect, but here is making a huge mistake, basically. To conclude the primitive of the attack, now we have a read primitive. We can read any address that we want. So we just need to break ASLR because we don't know where the process of Firefox is located. And it's quite simple now. You just need to, for example, allocate 1 GB of known text, let's say all A's. And then we start reading in a coarse-grained way, I don't know, gigabyte after gigabyte in the memory. And eventually we'll find that we leaked the intended sprayed memory. Once we have this coarse-grained, we just need to go page by page until we find the start of the spray. And after that, we break ASLR and we know that, for example, the Firefox memory will be on top of our sprayed memory. We're going also to show a full video of the attack. Again, this is the same setup of before, the victim page on the left, the attacker frame on the right. Exactly. We start by, again, this spraying of memory. So we have 1 GB of known text. And now, using FPVI, again, a division that type confuse Firefox to read arbitrary memory. We are reading in a coarse-grained way until we find our sprayed memory. And after a while, I mean, it takes a few seconds, exactly now is almost finished, we broke ASLR of Firefox. And now we are already leaking the entire Firefox process memory. Now we are just printing useful text, but in reality, in the background is reading a lot of memory of the Firefox process. And eventually, you see, exactly, we are leaking the secret page of the victim. Again, just by using a floating point division. It is quite crazy in our opinion. And if we let the attack runs for a bit, we also start leaking other stuff after the page. That is, for example, JavaScript probably of, we still don't know. This is JavaScript code. Because again, we completely broke the barrier. So now we can read the entire Firefox process memory. Now you may ask, what is the leakage rate? Well, it's quite high for this kind of attack. It's 13 kilobytes per second. And how can we defend against it? Well, there are multiple choices. The first one is to disable entirely these special floating point numbers. There are some registers in the floating point unit to do that. But it's not a viable solution because many programs actually works based on this representation. So we try to implement a compiler pass to basically serialize the processor pipeline to avoid this speculative execution. However, the overhead is quite significant. It's at least 53% on a heavily floating point suite. Exactly. So at the end, Firefox implemented a custom defense. It is basically a conditional mask of floating point results. So whenever you do a floating point division in Firefox, before actually getting the results, there is like an if condition checking that actually is not a non-result, so you're sure that even transiently this cannot be abused. Or simply, as Chrome is doing, set isolation. Every tab is a separate process, and you cannot cross this border. Now, I will present the last type of machine clear, that is memory disambiguation. And basically, when a load instruction is following a store instruction, which the destination of these addresses are not ready yet, there is a specific predictor in the CPU named the Memory Disambiguation unit that tries to predict if either these two operations will operate on the same address or not. So aliasing to the same address or not. Again, let's use a very simple example to explain this. A store followed by a load. Let's say that, again, the store address is not available yet. Maybe it's coming from a long operation in the pipeline. So at this point, the processor asks the predictor, look, I know I should wait the store to complete before doing the load, but can you predict for me if they are operating on the same address so I can parallelize and go faster? Let's say that the predictor will say, yes, they are not the same. You can do them in parallel or out of order. Well, obviously a predictor can be wrong. And if actually the address of the store and the load is the same, well, you need to execute before the store and then loading the newly stored values, in this case, hello. So the load highlighted in red will be executed firstly with a stale data, and later will be re-executed with the correct data. So here the invariant is that the processor really trusts this predictor, and basically the predictor will never make a mistake. And to violate this, again, you need a misprediction. So bringing the processor or the predictor in a state that is going to make a mistake. And the security implication is that it will transiently leak stale data. Regarding exploitation, this was already known in the past, was named Spectre v4. We presented also in this paper because we believe was kinda mistaken for a Spectre variant where it's on the branch misprediction. Here actually, if you think about it, it's on data misprediction, so you are mispredicting the data the processor is operating on. Now, yes, on our paper, I know 4 is already a lot, but in our paper there are even more, if you want to know about them. There are other strange conditions the processor must stop, flush the entire pipeline, and re-continue from the correct path. For example, exception, we have interrupts. There are other many types of microcode assist, but for that, please have a look at our paper. And now, back to Hany.
All right, so now that we've seen 4 types of machine clear, let's look at the big pictures of what we presented so far. We've seen a self-modifying code machine clear, where a store instruction causes a machine clear, triggering the pipeline flush of previously executed instructions. We've seen the memory ordering machine clear, where a processor violates the memory ordering model of another processor, flushing its pipeline again. The floating point machine clear, where we perform any floating point division with controlled operands, causing the processor to flush its pipeline again and re-execute the instructions. And the last one is the memory disambiguation machine clear, where we flush the pipeline from one load instruction that had loaded stale data. So how these types of machine clear perform compared to all previously known transit execution mechanisms. So here on the x-axis, you have the different types, the different mechanisms that can trigger transit execution, so speculative execution paths in the processor. And on the y-axis, we have 2 criteria. The top plot is representing the number of transient loads that fit within a single transient window created by a corresponding transit execution mechanism. And the bottom plot representing the leakage rate, how a specific transit execution mechanism performs in terms of leaking data. Here we have the flush and reload bars representing the architectural upper limit in terms of leakage rate. That we try to compare our leakage rate against. And then we have Intel TSX, BHT, and faults, which are the 3 ways, the 3 mechanisms that all previous transit execution attacks were relying on to create transient paths, where Intel TSX is obviously available only on Intel and is not supported anymore on recent CPUs. So before this, our work, an attacker would have been left only with a BHT, so mistraining a branch predictor, or causing a fault to create a transient path. But after our work, we're basically providing 5 new ways to create transit execution attacks, which are also available on AMD, which is quite powerful in terms of tools to reverse engineer the internal behavior of a CPU. When it comes to the number of transit loads, we can see that we measured more than 160 transient loads that can fit inside one single window of a self-modifying code machine clear. 160 loads that will never be committed architecturally and can leave a microarchitectural trace leaking memory. And this is with only one single self-referring code machine clear, which is really powerful. Another interesting number is that with a floating point machine clear, we can leak more than 4 megabits per second. 4 megabits with performing floating point operations. And this, again, will be transiently executed. It will never be observed on on the architectural execution, but on the microarchitectural level, it will leave an observable trace. And we can reach more than 4 megabits per second thanks to the determinism of a floating point operation. We're not mistraining. We're not wasting execution cycles on trying to bring the microarchitectural trace, the microarchitecture of a modern CPU to a known or a specific state. It's deterministic. We perform a floating point operation, and we have a transient execution path. So now that we have a clear image of all different transient execution mechanisms, we try to classify these to have a more systematic understanding of these of transient execution. And we start from two main subclasses of bad speculation. Bad speculation is let's say the top class representing this behavior on modern CPUs. And we have two main subclasses. The first one is control flow misprediction, and the second one is data misprediction. So control flow is speculating on the next instruction to execute. Data misprediction is speculating on the data, not code. Each subclass has its own predictor subclass. While control flow misprediction are failed attempts to speculate on the next instructions to execute, data mispredictions are failed attempts to operate on data that has been not validated yet. Then we have the exception subclass of data misprediction, which represents all the architectural exceptions that have been widely explored in previous attacks. And then we created this new subclass of data misprediction, which is called likely invariance violations, which represents all the architecture invariants that usually hold but occasionally fail. Like, for example, in the case of a floating point machine clear, where it assumes to be working on normal numbers, and that's correct because it works. Everything works fine in that case. But whenever a subnormal number occurs, then this invariant is violated. Another subclass of data misprediction that we observed creating transient execution path is interrupts, and more specifically, hardware interrupts. You can read this. You can read more about this in our paper. So we disclosed floating point value injection and speculative code store bypass to all major CPU, browser, operating system, and hypervisor vendors earlier this year. And we also observed that when it comes to store code bypass, speculative code store bypass, all Intel CPUs are affected, all AMD CPUs are affected. And regarding ARM CPUs, they are not affected because the coherency between data and code is explicitly left to the user. So it's not a vulnerability in that case. Regarding floating point value injection, again, all Intel CPUs are affected by this. All AMD CPUs are affected by this. And also ARM CPUs. We were informed after our disclosure that some floating point implementations on ARM processor are affected by floating point value injection. Mozilla confirmed the vulnerability and deployed a mitigation based on conditionally masking malicious NemBox floating point results, starting from Firefox 87 and on. And also the Zen hypervisor mitigated speculative code store bypass and released a security advisory following our proposed mitigation, which is basically issuing a serializing instruction after we store the new code in the case of SMC. So we make sure that code and data are coherent. And then when we try to call the new code, we actually also executing it on the microarchitectural level, and therefore avoiding a self-referring code machine clear. To conclude, bad speculation is not caused only by classic mispredictions, but also by architectural invariance violation, like the different types of machine clear that we presented today. These architectural invariants can be exploited, creating a new security threats like floating point value injection and speculative code store bypass. And we think that defenses from now on must focus on the wider meaning and the wider class of the root causes of bad speculation, which are not only avoiding mistraining a predictor. As we saw here, we can deterministically perform these type of attacks, and therefore the defenses must take this into account too. Here you can find different links to our paper, the code, and the exploit. And yeah, thanks for your attention. Now we can take any question you might have. Thanks.